Hello YouTube. In this video I'm going to outline the unification model of scientific explanation. This is defended most famously by Philip Kitcher. Now Kitcher begins from pretty much the same place as Hempel. He says that we look for explanations of things that are surprising, things that seem out of place, that we can't make sense of, and a good explanation shows us how this thing isn't surprising. Now recall that for Hempel, to explain something is to show that it was to be expected, and that's why he thought that explanation and prediction have the same logical structure. Well, on the unification model, to explain something isn't so much to show that it was expectable, rather it's to show that it's similar to something else that we're already familiar with. So the basic idea is that when we explain E, we take E, which we don't understand, and we show how it's like something else that we do understand. We explain E by showing how it fits into a broader pattern. We see a common pattern in what we initially thought were different situations. So you can see why this is called the unification model. We take two apparently disparate phenomena and show that they are connected. Furthermore, the more phenomena that we can subsume under a general pattern or a general system, the greater the unifying power of that system, so the greater its explanatory power. And this makes sense. We're saying that there is greater explanatory power for a theory that explains more phenomena. Now, we'll explore the details of this shortly, but you should see already this is a fairly intuitive account of explanation, and this kind of unification is also an important aspect of the sciences. Many of the important developments in the history of science have been cases of unification. Think of how Newtonian mechanics unified the terrestrial and celestial realms under a single system governed by the same laws of motion and gravity, or how Maxwell unified electricity and magnetism in the theory of electromagnetism, or the kinetic theory, for example, can be used to unify Boyle's law, Graham's law of diffusion, specific heat capacities, Brownian motion, and so on. So I'll just give this this as an example. Boyle's law is a gas law. It tells us that pressure is inversely proportional to volume when temperature and the amount of gas remain constant. So if you increase the pressure, you decrease the volume, and vice versa. Now, so that's one law. If you take Brownian motion, on the other hand, well, this is a phenomenon where if you have a very small particle suspended in a liquid or gas, that particle will jiggle about randomly, and it just seems to go on jiggling forever. It seems to be in perpetual motion, never running down. These two things, Boyle's law and Brownian motion, don't seem to have much to do with each other, but they're both explained by the kinetic theory of gases, which treats gases as composed of tiny, rapidly moving particles colliding with each other. And you can see how the explanation works in these images. So on the left here we have Boyle's law, and you can see if you decrease volume, the molecules will be compacted closer together, increasing pressure. For Brownian motion, the particle, the yellow particle here, is suspended in a sea of much smaller molecules, which are constantly colliding with it from random directions with random velocities, causing it to jiggle around. You can see then that much of the power of the kinetic theory stems from its application to many different phenomena that may initially have seemed to be unrelated. So part of the motivation behind the unification model is that what's missing in the deductive nomological model and even in the causal model is scientists aren't aiming merely for true theories of the world. Science isn't simply a matter of collecting together true statements. What we also want is to reveal the connections between them, and this is what explanation does. When we demonstrate this kind of connection, when we show that seemingly disparate phenomena fit the same pattern, we reduce the number of what we might call brute facts, facts that are unexplained. So we cannot know the worth of an explanation by considering it just in itself. We have to see how it fits into a more systematic picture. Let's try to put this in more formal terms. Broadly speaking, we have unification where we have a theory T, we have a range of phenomena P, which includes the explanandum, and we show how P can be derived from T. This shows how the explanandum plus other phenomena can be derived from T. The explanandum is therefore unified with P. So T plus the rest of P provides the explanation. We're going to outline the more specific proposal from Philip Kitcher. Kitcher's analysis is quite technical, but bear with me because I think the ideas here are fairly straightforward. Once you get through the technical language, it's quite a simple model. Kitcher's model is based on what he calls argument patterns. So what's an argument pattern? Well, first we have what Kitcher calls schematic sentences. A schematic sentence is a sentence in which some of the non-logical expressions are replaced with variables. Take, for example, organisms homozygous for the sickle cell allele develop sickle cell anemia. We can create a schematic sentence by saying organisms homozygous for A develop P. And you might actually make it even more abstract. You might say something like, for all X, if X is O and A, then X is P, or something like that. Obviously, you're not going to find totally abstract sentences in the sciences because such sentences wouldn't tell us anything about the world. Another example is, if the volume of the oxygen gas is decreased, its pressure will increase. The schematic sentence there might be, if the volume of X is decreased, its pressure will increase. Next we have filling instructions. Filling instructions tell us how to replace the dummy letters. In this example, A is replaced with the name of an allele and P is replaced with the name of a phenotypic trait. So a different way of filling out this schematic sentence would be, organisms homozygous for the BRCA mutation develop breast cancer. Next, schematic arguments. Schematic arguments are sequences of schematic sentences organised into premises and conclusion. And then a classification tells us which sentences are premises and which is the conclusion. It tells us what the rule of inference is and so on. Finally, then we have an argument pattern. This consists of a set of schematic sentences. So it consists of a schematic argument plus a set of filling instructions and a classification. And particular arguments in science will instantiate a general argument pattern. This is all very abstract, so it's probably helpful to look at a specific example. We'll take Darwinian natural selection. One of the many questions that concerned Darwin was to explain how adaptations arise. When we examine a species and we find that all members of the population share a particular trait, why is this? For example, we might look at a population of finches on an island and we find that they have longer beaks than the mainland finches. Why? Right? Why do all the members of this island population have longer beaks? Darwin gives us an argument pattern that we can use here. Here's how it works. So premise 1, the organisms in G are descendants of members of an ancestral population G star who inhabited an environment E. If you take a population of finches, there will be some population of earlier finches that they descended from. 2, among the members of G star there was variation with respect to a particular trait, such that some members had P, others had P1, others had P2, etc. Some finches had longer beaks. So in this ancestral population there was variation in the size of the beaks. Some of them had longer beaks, some of them had shorter beaks. 3, having P enabled organisms in E to obtain certain benefits, such that they survived and reproduced to a greater extent than organisms with P1 and P2, etc. So let's say that there's a certain type of food for the finch that's only found in deep crevices on trees. So only those with the longer beaks could reach the food. The shorter beaked finches could not, which gave the finches with the longer beaks an advantage. 4, P1, P2 etc. are heritable. 5. In each generation of the lineage leading from G star to G, the relative frequency of organisms with P increased. 6. The number of generations in the lineage leading from G, that should be G star to G. Sorry, I wrote that bit wrong there. So the number of generations from G star to G, because G star is the ancestral population and G is the current population, was sufficiently large for the relative frequency of P to increase to 1. 7. All members of G have P. This is a schematic argument, and I've suggested one way of filling it in with the Finch example. But here are the general filling instructions. So G is replaced with the name of a currently existing population, Finches, for example. G star is replaced with the name of an ancestral population, so this would be an ancestral population of finches. E is replaced with the name of an environment. We might be on, say, the Galapagos Islands. P1, P2, etc. are replaced with names for determinate forms of a trait. So longer beaks, middle-sized beaks, shorter beaks. And then the classification. In this argument, 1 to 4 and 6 are the premises. 5 is derived from 1 to 4 and 7 is derived from 5 and 6. This argument should be perfectly familiar if you read any biology. Today, after many years of biological development, it maybe doesn't seem all that special, but this is a very powerful argument pattern because it can be applied across the entire biological world to all different kinds of traits. We use this argument pattern over and over and over again, and in this way it unifies many phenomena. Furthermore, of course, Darwinian natural selection can now also be applied to explain many other things, the distribution of species or shared characteristics across species or the extinction of particular species. So the argument pattern can be modified, and as biology has developed, we have a much more sophisticated theory of selection than Darwin did. But this should give you some idea of how argument patterns work. And you can see how this applies to other examples. With Newtonian mechanics, for example, we derive facts about the moon's orbit using the 3 laws of motion and the law of universal gravitation. That same kind of argument, that same argument pattern is used to derive facts about falling objects here on Earth. And so in that way, Newton unifies the orbit of the moon and the planets with events here on Earth. One thing that I think is worth noting about Kitcher's model is that it really seems to match quite well how we go about learning scientific theories. A really important part of learning a theory in depth is performing exercises. Well, what does that involve? Well, when you read a physics textbook and then you work on the problems, you're learning how to apply, say, the Newtonian argument pattern to different phenomena. So anyway, the claim is that we explain a phenomenon when we derive it using an argument pattern. Of course, there are many different argument patterns we might use. In Darwin's time, there were plenty of competing theories to natural selection. So, how do we decide, right? Even today, there are true things we can say about the world, but that don't necessarily match Darwin's argument pattern. Kitcher says that the explanation is provided by whatever argument pattern is the best unifier. An argument pattern is a better unifier when it has smaller sets of premises and applies to a greater range of phenomena. Michael Strevens sums this up with the principle: the argument pattern that best unifies is the one that yields the most from the fewest. Many different phenomena derived from the fewest basic principles. This is a really important aspect of the unification model because it allows the model to deal with the difficulties that sunk the deductive nomological model. Recall the case of explanatory irrelevance, which I illustrated with the example of birth control pills. So the thought is somebody who explains why John failed to get pregnant by appealing to the fact that he's a male who takes birth control pills. This explanation is clearly defective, but why? Well, it's pretty clear that all males who take birth control fail to get pregnant. That's much more complex than the law. All males fail to get pregnant. And of course it's applicable to fewer phenomena because the vast majority of men don't take birth control pills. So an argument pattern that uses all males fail to get pregnant is going to be superior. Another problem that this model solves is asymmetry, illustrated by the flagpole example. The question is, how do we account for the asymmetry of explanation? The fact that the height of the flagpole explains the length of the shadow, but the shadow doesn't explain the height of the flagpole. Kitcher's claim is that explaining the height of the flagpole appeals to what he calls the origin and development argument pattern. On this pattern, the dimensions of any object are derived from facts about the conditions under which it originated, and then any modifications it underwent since its origination. So we're considering as an alternative the argument pattern that we might call the shadow pattern, where we derive the dimensions of objects from facts about their shadows plus the law of optics. If we reject the origin and development pattern and replace it with the shadow pattern, we will be able to derive far fewer facts. Many objects don't have shadows, so we just wouldn't be able to say anything about their dimensions. Or if they do have shadows, you can never get all the dimensions from the shadow. You would not be able to derive the width of the flagpole because different widths will be compatible with the same shadow. Similarly, the origin and development pattern can be applied to other properties like mass, which of course the shadow pattern cannot. So we can't replace the origin and development pattern, but another idea is, well, why not keep the origin and development pattern and then add the shadow pattern as well? So then we've got two argument patterns. Wouldn't that be more useful? Well, the trouble now is that we've violated the constraint of using the fewest principles. The origin and development pattern is already perfectly sufficient. It applies across the board to all objects. Adding the shadow pattern wouldn't allow us to derive new facts. It would only increase theoretical complexity. So we reject it. So this is, I think, quite a powerful theory. One thing that's maybe worth noting, an interesting consequence of this, is that James Woodward points out that this is what he calls a winner-takes-all conception of explanation. So only the most unifying argument pattern is explanatory. It's not that various patterns are explanatory, but some are more explanatory than others. Only one is explanatory. So strictly speaking, Newtonian mechanics is no longer explanatory because general relativity is more unifying. So Newtonian mechanics is not an explanation in any way at all anymore. It's clear that if we allow less unified argument patterns to be merely less explanatory, the solutions to the problems of explanatory irrelevance and explanatory asymmetry are lost. The shadow pattern would become explanatory. It would just be less explanatory than the origin and development pattern. Similarly for the birth control example. So if we want to avoid that, if we want to say that the shadow pattern just isn't an explanation, then the unification model requires this winner-takes-all conception. And some people may find this a little bit counterintuitive because it seems like Newtonian mechanics can still provide explanations. They're just not as good as the explanations provided by general relativity. But the unification model has to deny this. It has to say that only the best unifier, only the most unifying argument pattern can count as an explanation. So that's something that's worth bearing in mind. Now, another interesting aspect of Kitcher's views that I'd like to mention is his analysis of causation. This isn't an essential feature of the unification model, but as I think it's interesting, it's worth mentioning. So the causal model, which we considered in the last couple of videos, is intuitively appealing because it seems that there's a really deep connection between causation and explanation. And Kitcher agrees with this. He thinks that yes, right, that causation and explanation are deeply connected, but the causal model gets the connection the wrong way round. In fact, according to Kitcher, explanation determines causation. We say that X causes Y as a result of the fact that we use X to explain Y. So our judgment that the length of the shadow causally depends on the flagpole's height and not vice versa, that judgment is justified by or arises from the fact that height is used to explain the length of the shadow. due to the origin and development pattern. You know, the current properties of an object are derived from how it originated and the later modifications over time. Whereas we don't use the shadow pattern. So we don't say that the shadow causes the height. Argument patterns apply an order to the phenomena of the world, and this order is expressed in our judgments of causal dependence. This kind of view of causation will probably be quite appealing to an empiricist, because causality on this view seems is not a property of the world. It's not this strange metaphysical glue. Talk of causation is a result of our explanatory practices. So, you know, if you're inclined towards if you're inclined towards a more Humean view of causation, you know, you agree with Hume's criticisms of the concept of causation, but you can see the problems with the deductive nomological theory, then the unification model perhaps provides a nice way out, a nice option for you. One obvious concern here, though, is even outside of the sciences, we routinely make causal judgments, but we don't engage in working out argument patterns and deriving descriptions of various phenomena and so on. So, you know, how can this be, right? How can it be that judgments of causation arise from the application of argument patterns? Well, Kitcher says, you know, look, of course it's true we don't consciously use argument patterns. But his thought is that there are very general argument patterns that are implicitly adopted by society. So the origin and development pattern with respect to objects is a good example. All of us share a general theory of the world, a general theory of objects. It's not nearly as sophisticated as scientific theories, but it is still a kind of theory, and it includes these argument patterns that unifies phenomena. And that's where we get our idea of causation from. So I think that's kind of interesting. And that's all I've got to say today. In the next video, we'll look at some objections to the unification model, but that's all for now. Thanks for watching.